Okay, organic chemistry 2342. We're going to continue on with our chapters. This is going to be chapter 20, amines. We'll have 3 videos in the amine series, and this will be our first. Okay, so let's start with the nomenclature of primary amines. It's easy to name primary amines because we either can use their systematic or common name, and they're almost the same. In our systematic name, we want to use the longest chain or ring bonded to the amine. We want to take that alkane name, drop the E, and add the word amine to the end. And then all the other rules apply after that, okay? If we're assigning a common name, what we're going to do is we're just going to take the alkyl group that's bonded to the nitrogen and add the word amine. So if we look at the common and systematic names for the one with just a methyl group on it here, we have methylamine or methamine, if we're going to use the systematic name. If we look at the ethyl group, it's ethylamine or ethamine. If we have the isobutyl group, it's isobutylamine. And that would, of course, be 2-methyl-1-propanamine. And then, of course, with our cyclo compounds, name the cyclo first, drop the E, and add amine to it. So it's cyclohexamine. Okay, so now that we have our primaries named, let's go talk about our secondaries and tertiaries. When we talk about our secondaries and tertiaries, we have to think about the number of different carbon chains bonded to that system. So if we have the exact same alkyl chain hooked up, we get to use the di or tri as the name for the primary amine, and then we just add the word amine to it. Okay, in systematic amines, what we would do is we would take the longest chain and name that one first for the E, and take the remaining alkyl groups, and we have to add the letter N to show that that alkyl group is bonded to the nitrogen. This is unique to nitrogen, and so we can see as having those N's on the front of the name tells us that that alkyl group we're substituted with is actually bonded to the nitrogen. And then, of course, we use them in alphabetical order to assign them in order here. All right, so let's look at these last systems here and see about their names. So in this case, we have an ethyl and a methyl. So we would, in the common name, say it's ethyl methyl because it's alphabetical order, amine. But in this case, it would be N-methyl ethylamine because ethyl is the longest chain. So that's the ethylamine is the parent, and we have to name the methyl as the substituent. In this case, we have, in the second case here, we have 2 ethyl groups. So that would be diethylamine in the common name, or ethamine is our primary because it's our parent longest chain, and then we have to denote our alkyl group as being a substituent, therefore it's N-ethyl ethylamine. Okay, if we have 3 of the same, we can call that in the common name triethylamine. However, in the nomenclature of the systematic system, we're going to have to name it ethylamine, and then we're going to have to note the 2 other R groups that are on that nitrogen as N, N, for them both being on the same nitrogen, and diethylamine. If you have multiple nitrogens in the system, you have to actually number them so you can have N, N, and N prime, denoting that you have 2 or more nitrogens in your system. Notice in a systematic name also, if you have multiple different substituents, you have to name them in alphabetical order. So being that the propane is the longest chain, we're going to have that as the parent of propylamine, propanamine, and then we have to name the N-ethyl and then N-methyl. Notice the N has to come before the substituent because each of those substituents has to denote it's bonded to the nitrogen. Okay, let's move on from aliphatic amines to some of the aromatic amines and hydrocycles. As we learned in our benzene, we have common names for some of these materials, but we also have systematic names. So in the case of an amino group bonded directly with benzene, the common name is aniline, but we call that benzamine. It's in the systematic name, we take the parent and then add amine to the end of it. In the case of this N-methyl aniline, we have N-methyl benzamine. And for this toluidine, which is a common name for it, we have 4-methyl benzamine. Notice that the amine takes precedent over the alkyl group in this case because it's slightly higher than an alkyl group, but just below the alcohol group. So we need to note that. Notice ethers also do not change the parent name. Therefore, when we have this alkoxy group as a substituent on benzene, the parent becomes the benzamine, and then we have to have the ether as the substituent. So in this case, we have the 4-methoxy benzamine. Most of the heterocycles that contain nitrogens have their own unique names. And so we're not going to go into that in great detail, but I'm going to show you a few of those and how they're named. Okay, so the ones here at the bottom here, we've introduced pyridine in the aromatic chapter, as well as pyrrole. Both of these are aromatic heterocycles containing nitrogen. And whenever we have a heterocyclic compound, we always start with the heterocycle or the odd atom as the number one position. So in both cases, this is the one position of these two aromatic heterocycle rings. And then notice neither of these have unsaturations, and therefore they are aliphatic heterocycles right here. And so they also have different names. So in this case, it's papyridine, which is related to pyridine, and pyrrolidine, which is related to pyrrole. Okay. So amines have different properties, just like alcohols have hydrogen bonding. Amines also have hydrogen bonding. So in the case of primary and secondary amines where we do have a hydrogen bonded directly to the nitrogen, those do hydrogen bond. However, they are not as strong a hydrogen bonder as alcohols because the electronegativity difference between the nitrogen and the hydrogen is lower in amines than it is in alcohols. Therefore, they do hydrogen bond, but they do not hydrogen bond as strong. And therefore, they do not raise the melting point as much as with alcohols. Now note, once we get that third substitution on the amine, all we have is a lone pair left. We do not have a hydrogen that hydrogen bonds. Therefore, the benefit or the raised boiling point and melting point we get from that hydrogen bonding goes away and the melting point or boiling point drops, okay? Most amines are soluble in organic solvents, regardless of size. However, if they're 5 carbons or less, they tend to be water soluble because of hydrogen bonding. If they're 5 carbons more, they tend to be insoluble in water. Okay, so because of that lone pair in the amines, we have some acid-base properties associated with it. Okay, the first thing to realize is that the lone pair on the nitrogen actually is sp3 hybridized, okay? Which means the shape itself of the molecule is that trigonal pyramidal, okay? That lone pair takes up that third geometric slot, that fourth geometric slot, and makes it into a pyramid. And as such, unlike when we have 4 things substituted on carbon, where you would have to actually physically move an atom from one side to the other, all we're moving is electrons. Because we're only moving electrons, we can rapidly fold back and forth this system, and therefore tri-substituted amines are racemic because they can flip those electrons back and forth. All you're doing is moving, you're not breaking any bonds to do that inversion, okay? Now, that being said, when we quaternize the system and you actually have to move an atom back and forth, that means quaternary ammoniums can be chiral and they do not racemize rapidly, but they can if it's a proton, they can do it in a tautomerization effect. Okay, now let's talk about the relative basicities of amines. Okay, when we talk about basicity, instead of trying to use a pKb value or the log of the base equilibrium constant, what we would like to do is actually use the comparative value of the pKa of the conjugate acid. And by doing that, we can actually think about the basicity of the material. So basically, the higher the pKa of the material, that means it's a weaker and weaker acid, okay? So that is analogous to the idea that the higher the pKa, that means it's going to be a stronger and stronger base. So in a relative terms, the higher you are on the pKa scale, the stronger a base you are. The lower you are on the pKa scale, the weaker the base you are. So let's use that to our advantage and try to look at some of the different reasons why we can increase or decrease the basicity of these amines. So the first factor we have to do is, just like with carboxylic acids, there's an inductive effect. And in the case of nitrogen, by adding electron donating groups to the nitrogen, you can increase the basicity. The way to think about it is, the bigger that electron pair gets, that lone pair gets, the more basic it is. And so if you have electron donating groups, that lone pair gets a little bit bigger. If you have things that pull electron density away from that lone pair, it decreases the basicity. Which brings us to our first effect that decreases our basicity, resonance effect. If you can pull some of that electron density away from the lone pair and divide it over multiple atoms, then you are decreasing the basicity of the system. In aromaticity, we actually have two different effects there, depending on whether the lone pair is involved in the aromaticity or not. I'll talk about that on the next slide. The next thing to think about when we're talking about basicity is the hybridization. In the example of the pyridine, right here, where we have an aliphatic hydrogen here, this is sp3 hybridized nitrogen right here. But in the case of pyridine right here, it's actually sp2 hybridized. Because it's sp2 hybridized, it's actually less basic. The more S character you have, the more basicity you have. Okay, so now let's talk about aromaticity and basicity here. Okay, so I said that you have two possible cases here. In one case, we have where the lone pair that is dictating the basicity of the pyridine can be donated into the ring to be included in the number of electrons in the aromatizing electrons, like the 6 electrons in the case of these 5 and 6 membered rings, or they are not in the aromaticity. So in the case of pyridine right here, our lone pair is actually sticking out orthogonal to the pi delocalization cloud. And in that case, that means that lone pair, that basic lone pair, is not part of the aromaticity, and therefore it increases the basicity, okay? In contrast, if we look at parole, the lone pair is actually included in the 6 electrons to make that system a system aromatic. And when it's included in that aromatic system, that means it's less likely for that lone pair to bond to hydrogens. Okay, so that means that if we look at the relative basicities of all these different things, again, we're going to use the pKa value as our thing to look for. So the higher the number in our pKa of our conjugate acid, the more basic the material is. So if we look at ammonia, we have a nice intermediate value of around 9 in pKa. And the aliphatic components right here that have electron donating groups like the carbon here are more basic than ammonia by itself, okay? If we look at the aromatized ones where we can delocalize those electrons in the aromatic ring by donation, we actually see a decrease in the basicity down from that 10 number to the 5 number here. And when we compare the lone pair as being either donated into the aromatic ring or not donated into the aromatic ring, we can see a difference in the basicity there too. When they are not donated into they are not used to make that aromatic ring, we have a basicity of around 5. When they are used to make that ring aromatic, the basicity drops to 0.4, becoming much more acidic, therefore having less basicity. Now, once we get down to electronic drawing groups next to that nitrogen, like in an amide, they actually become much more acidic and much less basic. Okay, so let's talk about 3 things in the spectroscopy associated with them. We're going to look at IR, we're going to look at mass spec, and we're going to look at NMR. In the mass spec, we have a nitrogen rule, meaning that most hydrocarbons or hydrocarbons that contain oxygen have even mass numbers because the masses of the different atoms are even. But if we have 1 or any odd number of nitrogen in there, the mass of nitrogen is 15, and therefore our molecular ion peak will be odd. However, the fact that when you add an odd number and an odd number together, you get an even number, that means when you have 2 or multiples of 2 odd numbers or nitrogens in your system, the molecular ion peak becomes even again. So if you have an even mass in your mass spec, you either have only carbon, hydrogen, and oxygen. If you know you have a nitrogen and you still have an even number, that means you have an even number of nitrogens, 2, 4, 6. And if you have an odd apparent ion peak or molecular ion peak, you have an odd number of nitrogens. Okay. In the IR, we have a very good representation of whether you have a primary, secondary, or tertiary mean. Because there's a strong absorption in the 3,000 to 4,000 range for the amine nitrogen, if you have hydrogens on there, we will see it. In fact, if you have a primary amine, you have two hydrogens, and those two hydrogens are going to be bonded slightly differently, and therefore you're going to get two peaks. If you have a secondary amine, you only have one hydrogen on the nitrogen, and therefore you're going to get one peak. Once you make a tertiary amine, you have 0 hydrogens on there, and with 0 hydrogens, you have no peak in this range at all. So you can actually look for the functional group transformation going from primary to secondary to tertiary and see which peaks you have just by looking at your IR. Now, when we move to NMR, we have a couple different effects. The first effect is that if we have a hydrogen on that nitrogen, it can hydrogen bond just like an alcohol. That being said, we have a very broad range at which those hydrogens can be bonded to, okay? In addition to that, it can also hydrogen bond, and it can move around based on the concentration of the sample. If we're talking about a hydrogen bonded to a carbon next to a nitrogen, then we're going to look at it as just like being bonded near an alcohol or an ether, in the fact that it will de-shield that hydrogen, it'll move it downfield, and so we'll see that shift in the system. And likewise in carbon NMR, we will see the nitrogen, that electron donating effect, chemically shift it higher to in the 40 to 50 range. And then as we move away from the nitrogen, that effect gets lower and lower and lower. And just like in an alcohol system, if you add deuterium to the system, that hydrogen will slowly will proton exchange with the solvent and go away. In addition, just like in oxygen, the hydrogen on nitrogen does not split adjacent hydrogens in proton NMR. So let's take a quick look at this proton spectrum here. What we see here is that we have, these are equivalent hydrogens, and then this is a separate hydrogen here, but we have this third hydrogen here on this nitrogen. This one right here shows up as a nice broad peak, and if you look here, if we blow this peak up right here, we see that that is a nice broad peak for hydrogen here, shown in number C, letter C. In the A group here, we have a total of 6 of these hydrogens that are equivalent, and they are split by this B hydrogen here, meaning we get a doublet for all 6 of those equivalent hydrogens. And we have, again, the hydrogen here, even though it's 3 bonds away from this hydrogen on nitrogen, we do not get it split by that. It is only split by these 6 protons to give us a heptat or a multiplet right here. And notice it shifted furthest up because it's 3 bonds away from this hydrogen here, but it's bonded only 2 bonds away from the nitrogen, therefore it's shifted furthest up in the field, up to approximately 3. Okay, that is it for the introduction to amines. The next video is going to be on amine reactions.